Alright guys, today we're going to be graphing and transforming quadratic functions. When you're graphing a quadratic function, you always start with the parent function. In this case, our quadratic parent function is f of x equals x squared. Now, if you think back when we learned how to determine the vertex from standard form, we took our negative b value divided by 2a. Now we don't have a negative b here. We don't have a b here. We don't have we do have an a value of 1. But what we would do is we would say, since there's no b value, it's 0 divided by, well, anything is 0. So our x value comes out to be 0. Well, when we take that x value and we plug it back in, 0 squared is also 0. So that's where our vertex of 0, 0 comes from. Now we know that our slope, or we're actually going to use our a value as if it were the slope. Our a value is equal to 1. That means our rise is 1. So we would go up 1 and then over to the right 1. But we can also see that if we plug in 1 here for x, then we're going to get 1 for y. 1 squared is 1. Likewise, if we plug in 2 for x, here's 2. When we plug that in, we get 4 for y. And then do the reflections, and you see our parent curve. Every quadratic function refers back to the parent function, just like any function refers back to the parent. Now we see that our first transformation is a vertical shift, which is actually a slide or a translation on the graph. When we deal with a vertical shift, we are either adding or subtracting a number to the parent function, in this case x squared. So our vertical shift would be f of x equals x squared plus whatever the c value is. Now I've got two functions up here related to the parent function, which is in red in the middle. First function, f of x equals x squared plus 2. This tells us that we're going to simply go up 2 on this graph. So we would take our parent and basically shift it up 2 units. Alright, then we have f of x equals x squared minus 5. And what we would do here is we would simply take our parent and move it down 5 units. Nothing else changed. The width did not change. The way that this thing is facing, in terms of it facing up, did not change. All that changed is we slid the parent function up or down based on the c value. The next type of shift that we have is a horizontal shift. Again, notice I've got 3 graphs up here, the middle one being our parent graph. The first function we're going to do is f of x equals x plus 2 in parentheses squared. Well, just like we've always seen, whenever we're dealing with something involving x, usually there's parentheses involved, and we took the opposite of what was in the parentheses. So when we see x plus 2, we're actually going to move our graph to the left 2 units along the x-axis. Whereas if I see x minus 3, or x minus anything, we're going to move to the right 3 units. So you can see the orange graph is to the right 3 units, and the green graph is to the left 3 units. So in other words, we're moving in the opposite direction of the number that's in the parentheses. The next type of transformation we have is a reflection or a flip. Now, a flip is created or caused by the negative a value. Anytime you have a negative a value, your graph is going to be facing down. Flipped down. So in this case, f of x equals negative x squared. Takes our parent graph and just simply reflects it across the x-axis. For right now, we're not going to see any reflections across the y-axis. We will only do reflections across the x-axis. The next type of transformation that we have are stretches or shrinks. A stretch or a shrink, in this case, we're only going to deal with the vertical stretch or shrink. That is, I'm going to stretch this thing up as if I were to take a rubber band and pull it vertically. You would notice that the sides of the rubber band would become closer together, or more narrow, or steeper. We get a vertical stretch when our a value is greater than 1. This value can be fractional, but it has to be a fraction greater than 1, such as 5 over 4. This is an improper fraction, therefore it's greater than 1. A shrink is caused by compression. When we compress the graph, as if we're pushing down on it, the sides of the graph are going to become further apart or get wider, or you could say flatter. The slope of those lines would become flatter, if you will, of those sides, not lines, but of those sides would become flatter. We have a vertical shrink when our A value is between 0 and 1. This is how we write the notation for A being between 0 and 1. 0 is less than A is less than 1. So it's a fraction between 0 and 1. It can't be 1, it can't be 0, it's in between. So, for example, 1/5 or 1/4 or 2/3. If those are our A values, since these values would represent the rise, then we would have a wider graph. Let's take a look at an example. Here we have two functions, y equals 3x squared and y equals 1/3 x squared. Now for the 3x squared, our A value equals 3, which means it's as if our rise is 3. So relating this to the graphs, notice that the orange graph is our parent function. And we see that y equals 3x squared is inside of that parent function. Therefore, it is more narrow. Or you could think of the sides as being steeper due to the A value being a 3, as if my slope got steeper. So it's steeper and more narrow. In contrast, the function y equals 1/3 x squared has a rise of 1/3 because my A value is 1/3. Therefore, I have a rise of 1/3. So from my vertex, I would go up 1/3. That's my rise. And then to the right, 1 unit. So it's as if my slope is 1/3 over 1. So when I do that, up 1/3 to the right 1, and then reflect that point, what I have now is a wider graph. It's as if you took my original graph and you just pushed down on it and widened it out. Just like if you push down on a rubber band, the sides of that rubber band are going to widen from one another. You can think of it as being wider or flatter even. Right, flatter. Or compressed, because compression is what's actually happening when we shrink it. So these are the types of transformations that we will deal with. Now here is a complete problem, if you will. This has all 3 out of the 4 transformations that we will deal with. Alright, first of all, we've got the function 2/3 times x minus 2 squared plus 3, where our vertex is the ordered pair 2, 3. How do we know that? When we look inside parentheses, we take the opposite of what's inside parentheses for our x value of the vertex, and we take the number outside parentheses for the y value of the vertex, the 3. The only one we change the sign of, though, is what's inside parentheses. We also know that our A value is equal to 2/3. Well, if you look at the red function is our parent function. The new function is going to have a horizontal shift of plus 2. Hey, I'm going to the right 2. It's going to have a vertical shift of up 3. So I go up 3. Hey, there's my point. At 2, 3. Well, then I determine my other points by using the A value. So if my A value is 2/3, that's like saying that my rise is 2/3. So if I were to use this like slope, I would have 2/3 over 1 for my slope. Rise over run. This is my rise. This is my run. Well, a rise of 2/3 means I'm going to go up almost 1 unit. 2/3 of a unit. That's right here. And then over to the right 1. And then reflect that point. And what happens is I create a curve that's wider than my original curve. Now, I didn't draw this original curve very good. Let me make this thing a little bit more accurate than it is than I originally drew it. Okay. All right, let me get rid of that. All right, let's make this thing a little bit more accurate. So I need to go up 1, right 1. and therefore up 1, left 1, reflected. And then I would need to go to the right 2, up 4. That would be right here, approximately. Not going to be perfect. And then to the left 2, up 4. And I hope that you can see that those two curves have a different width. The green is a little bit wider, not much wider, but a little bit wider than the original function. So our 4 transformations are vertical shift, horizontal shift, reflection, stretch or shrink, and here we have an example of all but the reflection. The only thing different, if I were to throw in a reflected A value, in other words a negative A value, it would just simply face down. Now tomorrow we're going to do several examples, and we will practice this hopefully to where it's very, very clear.